This is an example of a rapidly varied flow application in which we have spillway. We have water coming down a spillway. As it comes down the spillway, of course, it's coming down as a supercritical flow. It's coming down really fast, large fruit number. It gets to the bottom of the spillway, and through conservation of energy, it's going to do what we call a hydraulic jump, or that rapidly varied flow, and it's going to jump from an original depth of 1.6 feet to some other depth. Okay, and there's several things we're going to calculate in this example. Of course, we will be calculating the depth at which it jumps to. We're also going to classify the jump, and then we're going to compute the energy that's lost from point 1 to 2, so the energy that's actually lost as it jumps. Okay, so for this first step with the classification, for us to classify this jump, we need to know the Froude number at point 1, at the point at which it's jumping. Okay. Now, I'm given that this is a rectangular cross-sectional channel, right? It's a 10-foot wide rectangular channel. We know the flow going through this spillway is 600 CFS. So the first thing I'm going to do is I'm going to calculate the velocity. I know I'm going to need that. So thinking back, if my flow at point 1 is equal to my velocity at point 1 times the area of the cross-section at point 1, I can then rewrite that as just V1 is equal to Q1 over A1. Okay, so I'll calculate that here. That's 600 cubic feet per second. Okay, the area, it's a 10-foot wide channel. Okay, and my depth of flow is 1.6 feet. Okay. So this gives me a velocity of 37.5 feet per second. Okay. So we knew it was going to be fast. As water's coming shooting down this spillway, it's moving at 37.5 feet per second. Okay. The reason why I needed that is I'm going to compute the Froude number at that point, so I can classify that jump. So the Froude number is defined as the velocity over the square root of g times the hydraulic depth. Now the hydraulic depth for a rectangular channel is just the depth of the channel. So we have all the terms that are needed in this equation. We have velocity of 37.5 feet per second. And then we'll go square root, we'll do 32.2 feet per second squared for g. And then we have a hydraulic depth of 1.6 feet. Again, that's just the depth of the channel, but it's rectangular. Okay. This gives me a Froude number of 5.22. Okay. Now with a Froude number of 5.22, if we look in your textbook and actually in the notes that I provided you, there's a classification based on your Froude number in terms of how they classify a jump. With this Froude number, that would be classified as a steady jump. And again, that's just basically looking at the table and based on your Froude number at that point, right at the base of the jump, you can just classify it as an oscillating or steady or strong. They have different classifications. Okay? So now that we've classified the jump as a steady jump, it has a Froude number of 5.22, let's go ahead and figure out the depth of the water at which it jumps to. So for that, we're going to use the formula that was derived. Okay, y2 is equal to y1 over 2 times the square root, all this is 1 plus 8 times the Froude number at that first point. So we needed that anyway, minus 1. Okay, so now we're just going to insert the terms. So y2, I'll have 1.6 feet for y1 over 2. And then I've got all this, I've got 1 plus 8 times the Froude number, which is 5.22. Squared, right? All that's the square root of all this, and then minus 1. Okay? This gives me a depth of 11.05 feet. So let's think about that. Okay? So it comes shooting down. We have 600 cubic feet per second flying down this spillway. At point 1, it's got a velocity of 37.5 feet per second. It's got a depth of 1.6, and it jumps almost 10 feet to a depth of 11.05 feet. So there's a lot going on with this jump. Clearly, there's going to be some energy losses as well. So for us to figure out the loss, what we need is we need the energy at each point. Okay. Now I'm actually going to start at point 2. Now that I know the depth of the flow at point 2, I'm going to calculate the velocity. With that, I can then go through and do the energy. So like I did over here, I'm going to use the same relation. I've got V2 is equal to Q2 over A2. Again, Q2, it's the same flow, assuming we don't have any water spilling over the side of the spillway, which would be 600 cubic feet per second. Okay, it's a 10-foot wide channel. And our depth at point 2, we just calculated to be 11.05 feet. Okay, so this gives me a velocity of 5.43 feet per second, which we need. So when we calculate the energy, the specific energy at point 2, that's going to be its depth plus the velocity squared over 2g term. Okay, we know the depth, we just calculated that to be 11.05. Okay, we've got the velocity of 5.43 squared over 2g. Again, g in this case is 32.2. And this gives me an energy of 11.51 feet. Okay, I'm running a little tight on the space there, but I think I got it. Okay, now let's figure out the energy at point 1. We can take the difference between the two to see what our energy loss is. So our energy at point 1 is going to be the same calculation, but just with the 1 terms, right? So it's the y1 plus v1 squared over 2g. Okay, y1 in this case was 1.6 feet. We've got a much larger velocity. That was the 37.5 squared over 2g. Okay, and this actually has an energy of 23.44 feet. So I know these two energies, the energy at each point. So my lost energy, or my head loss, okay, between those two, it's just going to be the energy between 1 and 2, which comes out to be 23.44 minus 11.51. My energy loss ends up being about almost 12 feet. 11.93 feet. Okay, so again, when it jumps from 1.6 feet coming at a velocity of 37.5 to a depth of 11 feet coming in at a velocity of 5.43, the energy loss associated with that rapidly varied flow, or the hydraulic jump, is almost 12 feet. It's 11.93. And with that, we conclude this example.